so evaluating the model. If we want to evaluate the model, we can evaluate it now on the test images and test labels. We're obviously going to get the same thing because the valuation is test images and test labels. So we should get the same accuracy as 67.35, which we do right here. All right, so there we go. We get about 70%. If you guys train this on 10 epochs, you should get close to 70. I'm a little bit lower just because I didn't want to go that high. And that is now the model. I mean, we could use this if we want. We could use predict. We could pass in some image and we could see the prediction for it. I'm not going to do that just because we've already talked about that enough. And I want to get into some of the cooler stuff when we're working with smaller data sets. So the basic idea here is this is actually a pretty small data set, right? We use about 60,000 images. And if you think about the amount of different patterns we need to pick up to classify, things like horses versus trucks, that's a pretty difficult task to do, which means that we need a lot of data. And in fact, some of the best convolutional neural networks that are out there are trained on millions of pieces of, sample information or of data. So obviously we don't have that kind of data. So how can we work with, a few images, maybe like a few thousand images, and still get a decent model? Well, the thing is, you can't unless we use some of the techniques that I'm about to show you. So working with small data sets. So just like I mentioned, it's difficult to create a very good convolutional neural network from scratch if you're using a small amount of data. That is why we can actually employ these techniques. The first one, data augmentation, but also using pre-trained models to kind of accomplish what we need to do. And that's what we're going to be talking about now in this second part of the tutorial. We're going to create another convolutional neural network. So just to clarify, this is created. We've made the model up here already. This is all we need to do it. This is the architecture, and this was just to get you familiar with the idea. So data augmentation. So this is basically the idea. If you have one image, we can turn that image into several different images and train and pass all those images to our model. So essentially, if we can rotate the image, if we can flip it, if we can stretch it, compress it, shift it, zoom it, whatever it is, and pass that to our model, it should be better at generalizing because we'll see the same image, but modified and augmented multiple times, which means that we can turn a data set, say, of 10,000 images into 40,000 images by doing 4 augmentations on every single image. Now, obviously, you still want a lot of unique images, but this technique can help a lot and is used quite a bit because that allows our kind of model to be able to pick up images that maybe are orientated differently or zoomed in a bit or stretched, something different, right? Just better at generalizing, which is the whole point. So I'm not going to go through this in too much depth, but this is essentially a script that does data augmentation for you. We're going to use this image data generator from the keras.preprocessing.image module. And we're going to create an image data generator object. Now, essentially what this allows us to do is specify some parameters on how we want to modify our image. In this case, we have the rotation range, some shifts, shear, zoom, horizontal flip, and the mode. Now, I'm not going to go into how this works. You can look up the documentation if you'd like, but essentially this will just allow us to augment our images. Now, what I'm going to do is pick one arbitrary image from the test image dataset, or test image, I guess, group of photos, whatever you want to call it. I'm going to convert that to an image array, which essentially takes it from the weird dataset object that it kind of is and turns it into a NumPy array. Then we're going to reshape this so that it's in the form 1, which essentially means 1, and then this will figure out what the rest of the shape should be. 1, and then plus the image shape, which is whatever this shape is. So we'll reshape that. And then what we're going to do is we're going to say for batch in dataflow gen.flow. We'll talk about how that works in a second. Essentially, this is just going to augment the image for us and actually save it onto our drive. So in this instance, what's going to happen is this datagen.flow is going to take the image, which we've created here, right? And we formatted it correctly by doing these 2 steps, which you need to do beforehand. It's going to save this image as test.jpg, and this will be the prefix, which means there'll be some information after. And it will do this as many times until we break. So essentially, given an image, it will do test 1, test 2, test 3, test 4, test 5, with random augmentations using this until eventually we decide to break out of this. Now, what I'm doing is just showing the image by doing this, and batch 0 is just showing us, that first image in there. And that's kind of how this works. So you can mess with this script and figure out a way to use it, but I would recommend if you want to do data augmentation, just look into image data generator. This is something that I just wanted to show you so you're aware of, and I'll just run it so you can see exactly how this works. So essentially, given an image of a truck, what it will do is augment it in these different ways. You can see kind of the shifts, the translations, the rotations, all of that. And we'll do actually a different image here to see what one looks like. Let's just do image, say 20. See if we get something different. So in this case, I believe this is maybe like a deer or a rabbit or a dog or something. I don't really know exactly what it is because it's so blurry, but you can see that's kind of the shifts we're getting, and it makes sense because you want to have images in different areas so that we have a better generalization. All right, so let's close that. Okay, so now we're going to talk about using, pre-trained models. Okay, so we talked about data augmentation. That's a great technique if you want to increase the size of your data set, but what if even after that we still don't have enough images in our data set? Well, what we can do is use something called a pre-trained model. Now, companies like Google and, TensorFlow, which is owned by Google, make their own amazing convolutional neural networks that are completely open source that we can use. So what we're going to do is actually use part of a convolutional neural network that they've trained already on, I believe, 1.4 million images. And we're just going to use part of that model as kind of the base of our model so that we have a really good starting point. And all we need to do is what's called fine tune the last few layers of that network so that they work a little bit better for our purposes. So what we're going to do essentially is say, all right, we have this model that Google's trained. They've trained it on 1.4 million images. It's capable of classifying, let's say, 1,000 different classes, which is actually the example we'll look at later. So obviously the beginning of that model is what's picking up on the smaller edges and, kind of the very general things that appear in all of our images. So if we can use the base of that model, so kind of the beginning of it, that does a really good job picking up on edges and general things that will apply to any images, then what we can do is just change the top layers of that model a tiny bit or add our own layers to it to classify for the problem that we want. And that should be a very effective way to use this pre-trained model. We're saying we're going to use the beginning part that's really good at kind of the generalization step. Then we'll pass it into our own layers that will do whatever we need to do specifically for our problem. That's what's like the fine tuning step. And then we should have a model that works pretty well. And in fact, that's what we're going to do in this example now. So that's kind of the point of what I'm talking about here, is using part of a model that already exists that's very good at generalizing and it's been trained on so many different images. And then we'll pass our own training data in. We won't modify the beginning aspect of our neural network because it already works really well. We'll just modify the last few layers that are really good at classifying, for example, just cats and dogs, which is exactly the example we're actually going to do here. So I hope that makes sense. As we get through, this should be cleared up a little bit, but using a pre-trained model is now the section we're getting into. So this is based on this documentation. As always, I'm referencing everything so you guys can go see that if you'd like. We can do our imports like this. We're going to load a data set. This actually takes a second to load the data set, I believe. Oh, maybe not. And essentially the problem we're doing is trying to classify dogs versus cats with a fair degree of accuracy. In fact, we'd like to get above 90%. So this is the data set we're loading in from TensorFlow datasets as TFDS. This is kind of a weird way to load it in. Again, stuff like this, you just have to reference the documentation. I can explain it to you, but it's not really going to help when the next example is going to be a different way of loading the data, right? So long as you know how to get the data in the correct form, you can get it into some kind of NumPy array, you can split it into training, testing, and validation data, you should be okay. And if you're using a TensorFlow dataset, it should tell you in the documentation how to load it in properly. So we'll load it in here. We're training 80% train. We'll go 10% for, raw validation and 10% for the testing data. So we've loaded that. And now what we're doing here is just we're going to look at a few images. So this actually creates a function. I know this is a weird thing. This is pretty unique to this example that allows us to call this function with some integer essentially and get what the actual string representation of that is, so the label for it. And what I'm doing here is just taking two images from our raw training data set and just displaying them. And you can see that's what we're getting here, dog and dog. And if I go ahead and take 5, we'll see these are what our images look like. Right, so here's an example of a dog. We have a cat, right, and so on and so forth. You get the point there. Now, notice though that these images are different dimensions. In fact, none of these images, other than these two, actually are the same dimension at all. Oh, actually, I don't think these ones are either. So obviously, there's a step that we need to do, which is we need to scale all these images to be the same size. So to do that, what we're going to do is write a little function like this that essentially will return an image that is reshaped. So I guess that is reshaped to the image size, which I'm going to set at 160 by 160. Now we can make this bigger if we want, but the problem sometimes is if you make an image that is bigger than, like you want to make your image bigger than most of your data set examples, and that means you're going to be really stretching a lot of the examples out and you're losing a lot of detail. So it's much better to make the image size smaller rather than bigger. You might say, well, if you make it smaller, you're going to lose detail too, but it's better to compress it smaller than it is to go really big. even just when it comes to the amount of training time and how complex the network is going to be. So anyways, that's something to consider. You can mess around with those when you're making your own networks, but again, smaller is typically better in my opinion. You don't want to go too small, but something that's like, half the size of what an average image would be. All right, so we're going to go format example. So what we're going to do is take an image and a label, and what this will do is return to us just the reshaped image and label. So in this case, we're going to cast, which just means convert every single pixel in our image to be a float 32 value because it could be integers. We're then going to divide that by 127.5, which taken is exactly half of 255, and then subtract 1. Then we're going to resize this image to be the image size. So sorry, the image will be resized to the image size, so 160 by 160, and we'll return the new image and the label. So now we can apply this function to all of our images using map. If you don't know what map is, essentially it takes every single example in this case going to be raw train, and applies the function to it, which will mean that it will convert raw train into images that are all resized to 160 by 160, and we'll do the same thing for validation and test. So run that, no issue there. And now let's have a look at our images and see what we get. And there we are. Now I've just messed up the color because I didn't add a CMap thing, which I think I needed. Where was the CMap? Anyways, you know what? That's fine for now. This is what our images look like. This is the resize. Now we get all our images 160 by 160, and we are good to go. All right, so now let's have a look at the shape of an original image versus our new image. So, I mean, this was just to prove that essentially our original shapes were like 262, 409 by some random values, and they're all reshaped now to 160, 160 by 3. 3 obviously is the color channel of the images.